In this video, we will cover Chapter 6, Benzene, and its derivatives. For Subtopic 6.1, Introduction. The learning outcomes for 6.1 Introduction is, to describe aromaticity, Kekulé structure, and resonance structure of benzene. First, let's take a look, why benzene is called aromatic compound.
Benzene is a hydrocarbon with a melting point of 8 degrees Celsius and a boiling point of 80 degrees Celsius. At room temperature, it is a colorless liquid with a characteristic strong odor. This odor was the reason why benzene and its derivatives were named aromatic compounds or arenes. Today, compounds are classified as aromatic not on the basis of their odor, but because of their structural features. Nonetheless, the name aromatic compounds is still in use.
An aromatic compound, arenes, contains at least one benzene ring, or other ring structure, that resembles benzene in its chemical properties. Initially, they are called aromatic because of its odor, but now aromaticity refers to the stability of compounds that are considered aromatic. These are examples of aromatic compounds, which are benzene derivatives. Criteria for aromaticity. 1. Cyclic, the compound must in cyclic structure. 2. Planar. All atoms in the molecule lie in the same plane. 3. Completely conjugated. Means that in compounds, it contains delocalized electrons, with alternating single and multiple bonds. And 4th, the most important criteria. Number of pi electrons, must satisfy Kekulé rule, 4n plus 2, pi. To satisfy Kekulé rule, the value of n, must be an integer, where the total of pi electrons, should be, 2, 6, 10, as stated in the table. Let's take a look at examples of compounds with single rings. We have benzene and cyclobutadiene. Both compounds are cyclic, planar, and completely conjugated. Now we need to determine whether they satisfy Kekulé rule. For benzene, the total pi electrons are 6, which the value of n will be equal to 1, an integer. While for cyclobutadiene, the total pi electrons are 4, which the value of n will be equal to 1 over 2, not an integer. Therefore, benzene is an aromatic compound, while cyclobutadiene is not an aromatic compound, as does not satisfy Kekulé rule. Next, let's take a look at examples with more than one rings. The compounds are naphthalene and anthracene. Both compounds are cyclic, planar, and completely conjugated. Now we need to determine whether they satisfy Kekulé rule. For naphthalene, there are a total of 10 pi electrons, which the value of n is equal to 2, an integer. While for anthracene, there are a total of 14 pi electrons, which the value of n is equal to 3, which is also an integer. Therefore, both compounds are aromatic compounds, as both satisfy Kekulé rule.
That Friedrich Kekulé, a German chemist living in the 19th century, was trying hard to understand the structure of the benzene molecule.
One day, when he was sitting by the fire and pondering on the problem, he dozed off. And he had a dream. He dreamt about atoms and molecules, dancing and twining in front of his eyes. As he wrote in his diary himself, "I saw larger structures of manifold conformation, all twining and twisting in snake-like motion. But look, what was that? One of the snakes had seized hold of its own tail, and the form whirled mockingly before my eyes." In this way, Kekulé arrived at the hypothesis that the benzene molecule has a ring-like structure, which was soon confirmed by experimental techniques.
In Kekulé description, the bonds between two carbon atoms is sometimes a single bond, and sometimes a double bond. Kekulé suggested that a fast equilibrium interconverts the two isomers, which still is the same structure. Benzene is actually a resonance hybrid of the two Kekulé structures, where the electrons in the pi bonds are delocalized around the ring, which we can draw the benzene structure either as Kekulé structure or as resonance hybrid.
All 6 carbon atoms are sp2 hybridized. In this type of hybridization, 3 sp2 hybrid orbitals and 1 unhybridized p orbital are formed. You may remember that 3 sp2 orbitals will be oriented at 120 degrees with respect to each other, forming a planar triangular arrangement. The p orbital is perpendicular to this plane. Each orbital contains one of the 4 valence electrons of a carbon atom. 1 sp2 orbital of every carbon atom forms a sigma bond with a hydrogen atom. The remaining 2 sp2 orbitals bond to adjacent carbon atoms. Because the geometry of bonds around every carbon atom is planar, the 6 carbon atoms bonded by sigma bonds form a planar, 6-membered ring. In this arrangement, the 6 unhybridized p orbitals are parallel to one another, and they can overlap side to side, in pairs, to form 3 pi bonds. However, there is no reason to think that double bonds form at the particular carbon atoms shown in structure A. Equally well, the double bonds could be arranged as shown in structure B. In reality, all 6 unhybridized p orbitals contribute their electrons to a continuous, torus-shaped pi cloud, encompassing all the carbon atoms. The presence of this sextet of delocalized electrons, distributed on both sides of the ring plane, is the most characteristic feature of aromatic compounds.
The circle, actually, represents the 6 p electrons, distributed over the 6 atoms of the ring, which are delocalized. That's all for 6.1 Introduction. Thank you for watching.